Today we're going to take a look at an organic molecule that most people know about, nicotine. Most people know nicotine as the ingredients in cigarettes that makes them so addictive, but why is that? To see why nicotine is so addictive, we have to look at its chemical properties. So let's start with a general overview of the molecule. So, the molecular formula for nicotine is C10H14N2, and there is its fancy chemical name right up here. And this is just a Lewis structure of the molecule to kind of give you a better idea of what it looks like. Here is a picture of nicotine made with one of the models that I can make. Here are the nitrogens, the black are the carbons, and the white are the hydrogen. As far as chemical properties go, some physical properties include that nicotine is usually colorless or pale yellow. However, it turns brown when exposed to air or light, which is why the end of a burnt cigarette looks brown. As it's a polar molecule, it's soluble in polar molecules including alcohol, chloroform, ether, petroleum ether, and kerosene. In addition, nicotine is combustible when it's exposed to an ignition source, so that's why when you light your cigarette, the nicotine combusts. It should not be stored with strong oxidizers or acids, and we'll learn why about that in a minute. So let's look at some of the functional groups or clusters of atoms that we see in nicotine. One of the nitrogens has a lone pair and is bonded to 3 other carbons, which is this one right here, and that one, we call it a tertiary amine. One of the carbons that is bonded to 3 hydrogens, which would be this one right here, and that is a methyl group. And another one of the carbons has 2 hydrogens bonded to it, these ones, as well as these ones and these ones, and those are methylene carbons. The other nitrogen over here is part of a 6-membered group, in which nitrogen is one of the members of the group and the other 5 are carbons. You can also see these double bonds here, 3 of them, and that group together is called a pyridine. Now, also remember here that even though these are drawn as double bonds, they're not really double bonds, and that negative charge is spread out across the entirety of this ring. Alright, and so we know that nitrogen has 5 electrons around it, and we can see that the 2 nitrogens in nicotine are actually very basic. They're willing to donate those electrons right there to other molecules to form bonds. So for an example, earlier we noted that we should never store nicotine with strong acids, and so an example of a strong acid would be hydrochloric acid, which we've shown kind of dissociated here. And what happens is that those electrons from the nitrogen will bond with the hydrogen to form a compound that's not nicotine. So that's why you don't want to store it with strong acids. In addition, nicotine could act as a good nucleophile during a nucleophilic substitution reaction. The nitrogen in the pyridine ring, which is this one right here, would bond to the electrophilic carbon center, which would give the nitrogen a +1 formal charge. The other nitrogen has too much clutter around its available lone pair, which would prevent it from binding to the electrophilic carbon center. However, this reaction is semi-unlikely to occur just because so much is going on around this nitrogen molecule, and it would be unlikely that the substrates would bump into each other in just the right way. So now let's look at some of the spectroscopy for nicotine. Looking at the infrared or IR spectroscopy, we can determine some of the functional groups or bond types found in nicotine that we mentioned earlier. Right around 3000, we see this narrow peak right here, which tells us there are carbon-hydrogen single bonds. Above 3000, there's a broad peak that tells us nicotine contains nitrogen single bonded to a hydrogen, which is this one right here. And the peak at 1677 indicates the carbon double bonded to the nitrogen, which is this one right here. And the peak at 1691 indicates carbon-carbon double bonds, which is that little one right there. Now looking at the carbon-13 NMR, we see 10 different peaks here. These 2 are really close, but there's 2, which tells us that all 10 of nicotine's carbons are chemically distinguishable from one another. That is that they're all in different chemical environments. The 5 peaks that appear further downfield, which are these ones over here on the left-hand side, they represent the carbons that are closer to the electronegative element of nitrogen, and because nitrogen is electronegative, it pulls the electrons in the bond with carbon toward itself and away from that carbon. Hence the carbon is deshielded, and it's much easier to make those carbons resonate, which is why they're downfield. The H1 NMR spectra, it tells us about the hydrogens in nicotine, and there's 9 different peaks here, and so that means that there are 9 chemically distinguishable hydrogens. Like the carbon-13 NMR, we have downfield hydrogens over here, which means that some hydrogens are very deshielded due to being close to an electronegative element. Also, this tall peak right here is one type of hydrogens that has the most number of hydrogens in that type, which is the 3 hydrogens of the methyl group. And last, looking at the mass spectra, we see that the largest peak, this little last one over here, is 162 grams per mole, which gives us the molar mass of nicotine. Now that we know a little bit more about the chemical structure of nicotine, let's look at how it functions in the human body. First, we have to understand how acetylcholine functions in the body because nicotine can stimulate the same receptors that acetylcholine can use, which are nicotinic receptors. Acetylcholine is released by some efferent nerve cells in the body. For example, it's released at the neuromuscular junction, which means that it controls skeletal muscle contraction. After acetylcholine crosses the synapse, it binds to the nicotinic receptors on the skeletal muscle, which are these guys right here, and it causes depolarization and contraction of muscle fibers. Nicotine, when added to the body by, say, smoking a cigarette, will also bind to these nicotinic receptors, causing even further depolarization. So why is nicotine so addictive? There are also receptors for nicotine in the central nervous system in the brain. When nicotine binds to these receptors, neurotransmitters such as dopamine are released and cause a feeling of relaxation and euphoria. Once people begin to smoke cigarettes, they become addicted to the added feeling of relaxation and often find that when they try to quit smoking, they become depressed or stressed out and unable to function. However, there is a point when too much nicotine can be detrimental to the body. When large quantities of nicotine are ingested, there might be so much nicotine binding to receptors that the skeletal muscle fibers are completely paralyzed. This is because the muscle fiber becomes depolarized and sends its action potential but can never repolarize due to constant stimulation from nicotine. If the muscle fiber cannot repolarize, no more action potentials can occur. This means that nicotinism, also known as overexposure to nicotine, can lead to paralysis of the central nervous system or autonomic nervous system, where nicotine is involved in transmitting action potentials at the ganglia of neurons. Severe symptoms can result, including nausea, abdominal pain, vomiting, diarrhea, and difficulty breathing. This is why it is so important to keep your e-cigarette fluid out of children's reach. Overall, the structure of nicotine causes it to be a good base. Its basic nature is why nicotine should not be stored with strong acids because it can react with hydrogen ions to form a new compound. In addition, its structure allows nicotine to bind to nicotinic receptors. In small quantities, the nicotine binding to nicotinic receptors can cause relaxation, euphoria, and improved memory. However, large quantities can lead to muscle paralysis and even death.